So temperature and the ideal gas law are the first topics we're going to look at in thermodynamics. Temperature, even though it seems like something pretty simple, took scientists quite a while to really understand fully. And the reason for that is because the full explanation of temperature involves understanding what's going on the atomic level, and for a long time we didn't know anything about atoms. So today we know that on the atomic level, solids look something like this, where the particles are locked into a lattice structure, and they are not completely still. They're still jiggling, vibrating a little bit, but they're not free to move very much. If you give them a bit more heat, then the temperature goes up and they're able to move around a bit more. They're still kind of clinging together, but definitely not as locked in as in a solid, and so then they're in the liquid state. And if you keep raising the temperature, you will get a gas where they're not sticking together at all. They are just flying around. And why not use a animation if we've got one? So here we've got our solid, and so the particles are kind of locked into this structure. If we heat it up a bit, they start vibrating a bit more, and eventually they kind of start coming loose, and you'll have a liquid. If we keep heating up our liquid, some of them will actually start flying off, and eventually if you give enough heat, they will just be bouncing around, and you will have a gas. Alright, even though we didn't understand temperature, we still used it quite a bit. Here's some pictures of some ancient thermometers. Ancient, I think these were like 1700, something like that. Blown glass, they made them pretty fancy looking. These were actually used in hospitals. It's a frog. I'm not sure if people liked frogs, found it comforting in a hospital, but anyway, they would tie this to somebody's wrist and actually get an estimate of their temperature from that. Today we use some more sophisticated means. So the old-fashioned thermometer, like those other blown glass ones I just showed you, they are based on the idea that if you heat up a liquid, then it will expand, and if you cool it off, it'll contract. And that's kind of easily explainable by this idea here, that if you heat it up, they start moving more, so they're bouncing off each other more, and they end up being spread out more. And that still works fine, but we have some more advanced things. This is called a bimetallic strip, not a whole lot more advanced. Instead of using a liquid that changes its volume, we use a metal, so a solid. And different metals expand at different rates. So with these, if you have this green metal that expands faster as a function of temperature than the blue metal, then when you heat this thing up, it's going to start bending or curling. And usually, if you have an old thermostat in your home, if you pop that lid off, you'd actually see a whole spiral of bimetallic strip. And what they would do is they'd have some sensor on the end. So when your furnace was, or your air conditioner was off, let's say your furnace is off and it's getting colder, then this thing is going to start coiling up, and then this connection here will touch some other connection, and then that will kick your furnace on until this thing heats up again and expands out, and then it disconnects and turns your furnace off. So those were pretty widely used up until, I don't know, the last 10-15 years. Here's another type of temperature measurement device called a thermocouple. These are used quite a bit in electronics and industrial applications. They respond a whole lot faster than these types of measurements. And what you do is you take two different types of metals, and there's a variety of different pairs of metals you can use for different temperature ranges. And if you join them at the end, you don't just twist them together like this picture kind of shows, but you actually have to weld them together. You usually kind of have a bead at the end there. Then they produce a small voltage because of the what we call the different work functions in the metal, which we're not going to get into those details. But as you change the temperature, it changes the voltage, and this is a really tiny voltage, like a millivolt range. But it's a real accurate and quick way of measuring temperature, real good for using in electronics. This other device has some similar performance, I guess. It reacts really quickly and used in a lot of electronic devices. It's called a thermistor, and that's play on the term thermal resistor. And so these have a bit of material whose resistance changes with temperature. And so instead of measuring the voltage on the ends of these wires like we did with the thermocouple, you just measure the resistance in these wires. And I know we haven't covered those topics, but you get the general idea. There's different ways of measuring temperature. Anything that reacts in a predictable way and changes some property as a function of temperature, we can use that to measure temperature. So now let's look at the temperature scales that we all know and love and talk a little bit of history of where these came from. So the Celsius scale, made by Anders Celsius, A-N-D-E-R-S, it makes a lot of sense. I think most people are aware that 0 degrees Celsius is freezing water, and that 100 degrees Celsius is boiling water. Nice and easy, no problems there. And Fahrenheit, on the other hand, I forgot his first name, sorry Mr. Fahrenheit. Did he just choose 212 and 32 for freezing and boiling because he's random like that? Well, he was kind of random and not quite that random. He also used 100 and 0 as his reference points. He just put the thermometer in a different environment to make those reference points. So let's back up a little bit actually. If I want to make a thermometer, what am I going to do? Well, I can just take a test tube or something full of some liquid, and if I stick it in some environment, if I'm Celsius, I put it in ice, and that liquid, say, is at this level, well, I make a little marking on my test tube, and I call that 0. Then if I put it in something warmer, like boiling water, and this is going to rise up, and now my fluid level is up there, I make a little mark on my test tube, and I call this 100. And as long as the fluid changes volume in a fairly linear manner with a change in temperature, then we can just divide this up into nice even divisions. We can call them degrees, and there you go, we have created a thermometer. So as I mentioned earlier, Fahrenheit did use 0 and 100. He just used different environments. So for 100 he used something that's not exactly 100, but it's close. Human body temperature. These were made a long time ago, just so you know. I've actually heard that 98.6 degrees is not the average human body temperature, even though we all use that. Some German physician got that number after measuring like 10 people or something like that. I don't remember if it's a little higher or lower, but anyway, Fahrenheit came up with 100, off by a little bit more. Then 0 degrees Fahrenheit, this is where he got a bit creative. He wanted to get a bit colder than freezing water, but he wanted it to be something that was easily reproducible. So he did freezing salt water. So some of you might know if you add salt, that depresses the freezing point. So he used salt water, which freezes at 0 degrees Fahrenheit. And then again, just divided this up into degrees, and there you go. Wonderful temperature scale. Okay, let's move on to the ideal gas law. Now you guys hopefully are fairly familiar with this after the lab, but let's discuss a couple of things real quick. So there it is in all its glory. PV equals nRT. P is pressure, V is volume, N is the number of moles. R is the universal gas constant, sometimes just known as the gas constant. And T is the temperature. This needs to be measured in kelvins. I guess I forgot to talk about Kelvin's temperature. Let's jump back to that. So when scientists started doing more accurate measurements of temperature and relating it to other quantities, they realized that freezing water didn't really have any fundamental importance in the physical realm, and so calling that 0 wasn't as useful as calling the coldest imaginable thing 0, and that is when something has no thermal energy whatsoever, and so we call that absolute 0. Absolute 0. And so for the scientists like the Celsius scale a bit more, so they based the Kelvin scale off the Celsius scale. They just shifted it down so it starts at absolute 0. So all you have to do is take the temperature in Celsius and you add 273, if you want to be specific, 0.15, and that will give you the temperature in kelvins. By the way, we don't call them degrees Kelvin, we call them kelvins. There's no degree for Kelvin. Fahrenheit does have an absolute 0 scale. It's called the Rankine scale. I don't know if anybody ever uses it, but it's out there. Okay, so back to PV equals nRT. We have to have that temperature in kelvins. N is the number of moles. I'm hoping that most of you are familiar with that, but I'll go over that a bit more in the calculations section. It's just a way of measuring the number of particles, and usually since the number is so huge, we divide it by a number, 6.022 times 10 to the 23rd, which is known as Avogadro's number, to make the number of particles a smaller number, since it's essentially like counting in dozens instead of individual donuts, only the number is a whole lot bigger than a dozen, but then we can not count each individual particle and just have a little more easy to work with number. A couple other things I want to say about ideal gas law. You might have, if you've had chemistry, you probably learned a bunch of gas laws, Charles' law, Boyle's law, and all of that. What's great about the ideal gas law is that all of those other laws pop right out of the ideal gas law. So I'm not going to even bother talking about them much or having you memorize them or anything like that. I just want you to get good at using the ideal gas law, and you can solve every gas problem from this, and you can derive those others. So for instance, Charles's law, if you remember, was V1 over T1 equals V2 over T2. And in this case, for Charles's law, we are assuming that volume and temperature are the only things that are changing, meaning that we're holding pressure and number of particles constant. So what we do is, if we take the ideal gas law and we move everything that is changing onto one side of the equation, so here's my ideal gas law, I'm changing volume and temperature, so that gives me V over T, and then I put everything that's constant on the other side, so I'm going to have N, R is always a constant, hence the name, constant, divided by P. Well, if I'm not changing any of this, I can just call it some constant C, not speed of light, but some other constant. And if V over T is equal to a constant, then anytime I change one of them, I change the other. So this quotient is always going to remain constant because it will always have to equal that same constant C. Same thing for Boyle's law. That one's P1 V1 equals P2 V2, right? Well, that comes from just holding all of this stuff constant and letting these two things change. So if I increase or decrease one, then I have to decrease or increase the other, do the inverse of whatever I did to the other. So that's really all the concepts regarding the ideal gas law. Oh, I've got to better play with my little ideal gas applet thing. This and the other one are both found on the PhET website. So if we put some particles into a box, you can choose to hold one of these constant or not, but this is just kind of showing you how gases react to changing different physical conditions. So if we add heat, so we're changing T in PV equals nRT. We're not changing N or R, so either P has to go up, which it does, or the volume has to go up. This guy here is keeping the volume from changing, so the pressure has to go up. Now, if we also decide to change the volume, we compress it. Pressure and temperature can both go up if we don't hold one of them constant. Anyway, you can play around. Gases kind of are fairly predictable and intuitive once you play with them a little bit. Okay, see you in the calculations. Bye.